So now we also want to look at examples of the density function and continuous random variable, as well as the continuous distribution function. And for that, I have brought two examples that clarify the relationship. On one hand, I have brought the so-called uniform distribution. You can see the following here. The density function is given as f of x, which is what we need to integrate. It is defined piecewise, and above all, it is for the interval from a to b, where I should perhaps add that a is less than b, and both are real numbers. And the density function has the constant value of 1 divided by b minus a, and otherwise, outside of this interval, the density function is 0. Let's sketch this out to better understand the whole concept. So here we have our x-axis and our y-axis. And what we are going to do now is, let's assume this is a and, this is b. I will make the function degrees red. So we know that to the left of a, the whole thing is 0. And to the right of a, it is also 0. And within the interval a, b, there is a value which is constant. Let's say it is here. And then there are 2 jump points here. And this value is 1 divided by b minus a. And what is important here is that we have learned that in a continuous distribution, the continuous distribution function is continuous. This here is the density function, which is not continuous. As you can see, it has this jump discontinuity here at a and at b. And we will take a look at how the distribution function looks here now. Before we do that, I want to show you that the distribution function is indeed a density function. And for that, we need to look at whether, when I take the entire area, it equals 1, because that is important for a distribution function. As x approaches infinity, the value is 1. Therefore, we need to check whether this area here is 1. And how large is this area? Well, it is a rectangle, and one side length, this one here, is b minus a, and this one here is 1 divided by b minus a. You can already see that the total area is then 1 divided by b minus a times b minus a, which is exactly 1. And there you can also see why we have now chosen this value of 1 divided by b minus a. We have chosen it in such a way that the area has the value of 1. And the question now is, what is the distribution function? And there are now 2 ways to approach this. One way would simply be through integral calculus. So that would be the integral from minus infinity to x. F of t dt. Yes, I wrote t here so that we have a different variable name than the variable name x, because that one appears here. However, we can make this a bit simpler in this case by simply calculating the areas. And what we see here now is that we have a piecewise defined density function. This means that, in general, the distribution function is also defined piecewise. And I will perhaps write down the sections here. The first section is relatively easy, as it is essentially when x is less than or equal to a. So that is everything that is on this page. And that is relatively simple. So we need to calculate the area up to a from minus infinity to a. However, since the function itself is 0, the area is also 0. And the other section is also relatively simple, namely that when we are greater than b, the area we see is simply the total area of the rectangle, and we have already calculated that, which is 1. That means the interesting question is, what happens exactly between A and B? That means, let's quickly visualize this. I'll use the color red here. Let's imagine we are in this situation here. This is our x. Then we need to determine the area of, I'll shade this in, this part rectangle here. And we can do that again by multiplying height by width. Let's take a look at the height is again 1 divided by BA. 1 divided by BA times, and the lateral area here is now XA. And that is then the result, which could be summarized now. But essentially it is that for x in the interval from A to B. And now we can consider what happens at these points A and B right. And if you substitute then you can see that the function is 0. And when you substitute b, you can see that the function is exactly 1. From this, you can also see that the whole becomes continuous. You can also try to sketch the distribution function, perhaps as a task. And now the question is, in what situations does such a uniform distribution occur? In reality, indeed. And for example, if you imagine the following, imagine you have a bus that arrives every 15 minutes. You are sitting at the bus stop, but you have no watch, and you also have no schedule. And you should consider how likely it is that the train will arrive in the next X minutes. This is exactly the situation we are in, because all possibilities from 0 to 15 minutes are equally likely. This means that it would be a situation where A equals 0 and B equals 15, which makes it a very concrete and relatively realistic example where we have now determined the distribution function. So, now let's take a look at the reverse problem. We have a distribution function given and want to determine the density function. So we know that we have our f of x given. Let's take a look. And therefore want to determine the density function. This can no longer be done quite as easily by calculating areas. For this we need to differentiate because the density function is the derivative of the distribution function. So you need to remember how we derive the function. Before we do that, we want to briefly visualize the distribution function again. What does it look like? I'll do that again in red. On one hand, for x less than 0, the whole thing is easy again, so we are at 0. This also fits because when x approaches negative infinity, the distribution function becomes 0. That is exactly what we want. So, as x approaches positive infinity, let's take a look at this term here, which is 1 minus e raised to the power of minus kx. By the way, k is a real number. Let's, for instance, envision it as a positive one. So, once again, when x approaches infinity, e raised to the power of minus kx is the number approaches 0. E raised to the power of minus kx approaches 0, and 1 minus 0 approaches 1. So, let's assume k is a positive number. Okay, that means we have an asymptote at 1. That's good because we want that. Exactly. One distribution function has the property that it approaches a limit of 1 at infinity. So, what happens at 0? Let's take another look at that. If we substitute above, then we have e raised to the power of minus k times 0, which is e raised to the power of 0, which is 1. And 1 minus 1 is therefore 0, so here we are. And in between, we have something like this. The graph has an asymptote at 1. So this is our distribution function. Now we want to determine our density function. That is, we take the function 1 minus e raised to the power of minus kx and want to find the derivative. How does that work again? So we first need the derivative of sums, the sum of the derivatives. That means we can differentiate each summand. First, we have the summand 1. The derivative of 1 is 0, so that cancels out. This means we only have the derivative of minus e raised to minus kx. So we can definitely factor out the minus. That means we need to differentiate minus e raised to the power of minus kx. And perhaps you still remember how to do that. You need to apply the derivative rule for chain functions, meaning for the chaining of functions. First, you differentiate the e function, which is again e. And then you need to multiply the derivative of the inner function. The inner function is minus kx, and its derivative is minus k. So we end up with minus times minus k times e raised to the power of minus kx. So this is our density function. And for that, you need to mastering the differentiation of functions. Now the question is there a suitable example for that as well? And that would be the case. For example, if you are dealing with the lifespan in years of components, then it is such that when they fail, they are subject to a distribution function or density function. So those were two examples. Once for the direction I have a density function given and want a distribution function, but also I have a distribution function and want a density function. And finally, for this chapter, we want to deal with the concepts of quantile and independence. This time not of events, which we covered last week, but of random variables. Until then, take care.